Okay, today's topic of discussion is Bezier SP-line curves or the Bezier curves. Basically, this Bezier SP lines have number of properties that make them highly useful and convenient for curves and surface design. And they are also easy to implement. They and then these SP-line curves, they are widely available in various CAD systems and general graphics packages and assorted drawing and painting packages also. Bezier curves sections can be fitted to any number of control points. Although some graphic packages limit them to, they limit the control points to 4. Basically, when I say control points, you might be wondering what exactly is the control points. For example, let us say I have these points. These are called as control points. Let's call it as P1, P2. Join this from, let's say the curve which starts from the first point, pull towards the second point and tilted towards the last point. We call this as the curve, which is nothing but the Bezier curve for us. And the degree of Bezier polynomial here is determined by the control points along with the position also. Here position also matters for us. Now let us first write some Bezier curve equations and then understand what exactly it is. First, let us start in the general equation, which we write it as n plus 1 control points. And the control point position, let us denote it as pk, and each pk will have the value of xk, yk and zk, and the value of k which varies from 0 to n. And these coordinate points are blended to reduce into the position vector, which is represented as p of u. That is the position vector which describes the path of an approximate Bezier curve function between p naught and pn. So p of u can be defined as summation of k varies from 0 to n pk, which is the position. Then we have bez kn of u, where the value of u varies from 0 to 1. Let us call this as equation 1, which is the general equation. Now let us see what exactly is this BEZ. So I have this BEZ Kn of u, which we call it as the Bezier blending function, which uses the Bernstein polynomials. That is, it is called as the Bezier blending function, and it uses the Bernstein polynomial. And it is basically defined as BEZ Kn of u, which is equal to C of n into k into u power k into 1 minus u of n minus k. So let us call this as the second equation. Now let us try to understand what is this C of nk. Basically, it's the binomial positions or the coefficients. So I'll call it as nk, which is equal to n factorial divided by k factorial into n minus k whole factorial. Now we can represent this equation 1 using a set of 3 parametric equations for individual coordinates. What are those individual coordinates? That's nothing but we have this. These are the individual coordinates for us. So we can write it as x of u is equal to summation of k equal to 0 to n x k bez kn of u. Similarly, you write it for y. Y of u is equal to summation of k is equal to 0 to n y k b is z kn of u. Similarly, z of u is equal to summation of k equal to 0 to n z k b is z kn of u. So you're going to write it in terms of 3 coordinate values. So one more important equation or one set of important equation for us. Bezier curve is a polynomial of degree which is one less than the number of control points for us. For example, if I have 3 control points, then degree equal to 2, which is a parabola, or you're going to generate a parabola for that matter. If you have a 4 control point, then the degree is equal to 3, which generates a cubic curve. Let us hear some examples. Let me take the example of two-dimensional curves. Let me start with 3 points for us. I'll say I have P0, P1 and P2, which is 3 control points. Let us join these control points with the dashed line. My Bezier curve starts with first point, moves towards the second point and tilts towards the third point. So this is the curve this is the example of the first case, that is the parabola. Now let us take the next example. I have P0, P1, P2 and P3. Now if I join the control points with the dashed lines, now the Bezier curve starts from P0, move towards the second point, then towards the third point and then towards the last point. It looks something like this, very decently done. Now let me take an example with 4 points. I have P0, I have P1, I have then P2 and then I have P3. Let me join all of these, something like this. Now if you draw the curve, see, it starts from P0, moves towards second point, third point and then the ends here. So you can see the difference here. There is a difference. It's not as tilted. Somewhere it looks like this for us. That is something like this. Yeah. Let me take one more example. P0, P1, then I take P2 and then some P3. Let's say I join these like this. Then my curve would be from here to here and then comes here. So it looks something like this. Now if I draw it with a 5 points, let me take an example which I have P0, I have P1, P2, P3 and P4. Join all of these lines. Points are like this in the sequence. Draw the curve now. Here you go. Then you move towards the third and then comes somewhere like this. So I'll say something like this. Now these altogether represents the two-dimensional Bezier curves which are generated with 3, 4 and 5 control points. And dashed lines are used to connect the control points positions for us. So recursive calculations can be used to obtain successive binomial coefficients values. For example, like if I write C of nk, then it can be written as n minus k plus 1 divided by k C of n k minus 1 for n greater than or equal to k. So the Bezier blending function, it also satisfies the recursive relationship. Or if we recollect the blending function, it is written as Bezkn of u, which is C of nk u to the power of k 1 minus u to the power of n minus k. This was our blending function. Now, if you want to write it using the recursive relationship, then it would be written as Bezkn of u, that is 1 minus u Bez k comma n minus 1 of u plus u into Bez k minus 1 n minus 1 of u, where the k lies between n and 1. This is one more important equation for you to recall. We can also write Bez k comma k equal to u of k. That is, if we substitute this value in this equation, we get it as, first let us calculate c to the power of nk, which is equal to n factorial divided by k factorial into n minus k factorial. So what is the value of n and k here? That, I mean, Bz of k is nothing but k and k for us. So that becomes, so this becomes k factorial divided by k factorial into k minus k whole factorial, which will be equated to 1. Similarly, what is the value of u to the power of k in our first equation, that is the blending equation? So that remains u c to the u power k itself. Then let us take 1 minus u n minus k. So here, if I take this k minus k, so anything to the power of 0 is 1. So we are going to get it as Bez kk is equal to uk. So same way we can write it as Bez 0 comma k is equal to 1 minus u to the power k. So here we have 0 k. So instead of writing Bez of kn, we are calculating it as, it is written as Bez of 0 and k. So it means these will have these values. So if we get, I mean, substitute, we will get it as c of nk is equal to n factorial divided by k factorial into n minus k whole factorial. So it becomes k factorial divided by 0 factorial k minus 0 factorial 1. So 0 factorial is equal to 1. So this becomes k factorial divided by k factorial, which is equal to 1. So similarly, this becomes u power k. So if k value is 0 for us, so u power of 0, so this becomes 1. So next we have 1 minus u. So here I have n minus k. K value is 0 for us, so we get it as, if you can see, if I substitute, I'll get it as 1 minus u to the power of, yeah, just going back here, I have 1 minus u, this k is 0, so this becomes 1 minus u to the power of k. So this is nothing but going back here. So it is very important for you to remember all of these. Yes, next let us move and understand some of the properties of Bezier curves. The very first property of the is it connects the first and last point for us. If you remember the examples that we had taken, it starts with the first points and then ends with the last control point. So the basic characteristics can be written as P of 0 is equal to P naught and P of 1 is equal to P of n. Let me take this as equation 1. The values for the first parametric derivative, okay, here is the first derivative of a Bezier curve can be determined as P dash of 0 is equal to minus NP naught plus NP1. So this becomes P dash of 1 is equal to minus n into Pn minus 1 plus Npn. So this can be easily written as, that is after simplifying, I could write it as is equal to Np1 minus Np0, which becomes N of P1 minus P0. So here P dash of 1 is equal to Npn minus Np of n minus 1, which becomes N of Pn minus n. So this is what, now the above expression shows that the slope or the beginning of the curve is along the line joining the first two control points here. And similarly, the slope at the end of the curve is along the last two endpoints. That is what we are trying to see here. Now let us look at the second derivative of the Bezier curve, which we write it as P double dash of 0 n into n minus 1, which is P2 minus P1, which is the first point, minus P1 minus P0. Okay. So this P double dash of 1 will be equal to P of n minus 1. So this becomes P of n minus 2 minus P of n minus 1. So next point, so this becomes P of n minus 1 minus Pn. This is the second derivative. Now let us look at the second property. It says that the Bezier curves lies within the convex hive of the control point. That is, if I take this example, here this curve is lying with this boundary. So it says, what we are trying to say is it always lies within the convex hull of the control point, or you can also say that convex boundary of the polygon. Because of this property, the Bezier bending function are always positive or equal to 1. That is Bez k of n u, where I'll say summation k equal to 0 to n, which is equal to 1. This is our second property for us. Basically, it's the weighted sum of the control points. The convex hull property of the Bezier curve ensures that the polynomial smoothly follows the control points without any erratic oscillation. Now there are some design techniques which can be used with the Bezier curves. Let me write this as the design techniques for the Bezier curves, or design technique using the Bezier curves. For example, if I take point P0, let me take point P1, and let me take point P2, and then let me take point P3, and somewhere here P4. Let me take one more point P5, which will overlap with P0. That means P0 and P5 are equal. Now if we join this, basically starts here. So I'll say go here, then comes here. Now if I try to draw the curve, with we are starting from the first point. So first, second, third, and then come and end up. This is the first property which we have already seen. So what will happen is, this is called as the closed Bezier curves for us. The closed Bezier curve. And this is generated when we set the last control point as the first control point. Similarly, I can set multiple control point at different positions. For example, let me take this as, I'll take P0 here. I have P1, and let me also take this as P2. It means that it contains more weight because it has two control points here. And let's say I have P3 and P4. If I join this and this becomes 1, so here I have, and here it ends. Curve starts from the first point. Here, since the weight of this point is more, this is more tilted towards this and move towards here and then comes back here. So specifying the multiple control points at a single coordinate position gives more weight to that position, so the resulting curve is more pulled towards that position. And to fit the Bezier curve to any number of control points, it requires the calculation of a polynomial function of higher degree. Now let us see the cubic Bezier curves. If you recollect the cubic Bezier curves, we remember it requires 4 control points. So I'll say I have the cubic Bezier curve. So we have n is equal to 4. The 4 blending functions for the cubic curve will be written as Bez of Kn of u will be written as C of Nk into u to the power of k into 1 minus u to the power n minus k. We have already seen this equation, which is the blending equation. Since it is cubic, n equals to 3. That means though it is control point, it is 3 for us. So I'll say Bez of 0, 3 for us. So it becomes 1 minus u to the power 3. How are we getting this value exactly is, let me substitute and see what exactly is that. K value, that means your k value is equal to 0 and when value is equal to 3. Now if I calculate C of Nk, which is equal to C of 3, k value is 0. So what is the value of C of Nk? It is n factorial, 3 factorial, so 0 factorial into 3 minus 0 whole factorial, which is equal to, which is evaluated equal to 1. Now if I come to the u to the power of k value is equal to 0, to power of 0 is equal to 1. Next we have the third term, which is 1 minus u to the power of n is 3 here, n minus k, so 3 minus 0, so which is equal to 1 minus u cube. So basically that is what I have written here. Similarly, you can calculate Bez of 1, 3. So this is equivalent to 3u into 1 minus u square. You can substitute the values like this and find out, you will get this. Similarly, if I compute Bez of 2, 3, then I'll get it as 3u square of 1 minus u. Next, if I take Bez of 3, 3, then that is equal to u cube. All these values can be derived by substituting the value of n and k in this above blending equation. You can just do that and test it out. Now the cubic Bezier curve always begins at the control point P0 and end at the control point P3. Because we have 4 control points for the cubic Bezier curve, which is P0, P1, P2 and P3. So it indicates we begin here and ends at P3. So the other Bezier functions here is Bez of 1, 3, Bez of 2, 3, that is the in between, and Bez of 3, 3. This, which are the in between points which influence the shape of the curve, that is the intermediate values which design the curves for you. And lastly, we have the Bezier curve, we have Bez of 3, 3, which becomes the ending point. Basically, if you recollect when I had gone one example where I had P1, P2, I have P3 and here P4 which is P0. We know the shapes were different basically. Why? Because here it is more tilted, here since the weight is more here. So we need to understand that the intermediate values determines the shape of the curve for us. And then now let us go to the blending function, which is written as Bez of 1 comma 3. It is maximum at u is equal to 1 by 3. Similarly, Bez of 2 3 maximum at, that means it will have the maximum value at u is equal to 2 by 3. So the Bezier curves do not allow for local control of curve shapes. If any one control point is repositioned, then the entire curve is affected. Now let us see how we are going to draw the graph for this. Let me take it here. Here I have 0, point 2, 0.4, 0.6, 0.8 and 1. Say this is 0. I'll say 0.2, 0.4, 0.6, 0.81. Okay. Now let us say if I am going to plot it for Bez of 0, 3. Basically Bez of 0, 3 will start from 1, because we have written it as this is equivalent to 1 minus to the power, cube. So if equals 0, then it will have the value 1. So if we go on substituting the value of u, this equation will vary from 1 and it will end up here somewhere. In that is, if you want to draw it for the second case, let us call it as Bz of 1 comma 3 of u. The shape of the curve will be in this case we have already written here is 1 of 3 is maximum when the value of u is 1 by 3. So in that case, if I take it as 0.3, then the curve somewhere would be, so if I substitute this, I'll get it somewhere, I think somewhere like this. And it is going to end up at 1 for us. Similarly, if I plot it for Bez of 2 comma 3 of u, this graph is as usual 2.4, 0.6, 0.8 and 1. Similarly 0.2, 0.4, 0.6, 0.8 and 1. We have already written that in this case it is maximum at 2 by 3, which is equal to 0.666. I think somewhere here, somewhere if you start with the first point, that is Bez 2 3 of u. So if to start from here and let's say somewhere here, it is at the highest, and then here, which is, and then comes here, and the last curve for us is Bz of 3 comma 3. So let us draw the graph. Here I have 0, 0.2, 0.4, 0.6, 0.8 and 1. Similarly 0.2, 0.4, 0.6, 0.8 and 1. So let's say this is for Bez of 3 comma 3 of u. So basically it goes somewhere like this infinitely. It goes infinitely because we have written Bez of 3 3 is nothing but of u, we have computed the value. If you look at the value, it takes it infinitely for us. So it's very important for us to plot the graph at the end of the Bezier curves for. So at the end of the cubic parameter, so if you look at the end of the cubic curve, the parametric derivative are p of 0, which is equal to 3 of p1 minus p naught, and this as p dash of 1 is equal to 3 of p3 minus p2. If you recollect, the first derivative was written as n of p1 minus n of p naught. Here the value of n in this case is 3, so I have written it as 3 of p1 minus p naught. And if you return the second one, we had written it as npn minus npn minus 1. So we have the value of n is 3 for us, so 3 of p3 minus p2 for us. That is, we have just substituted the values in the earlier equation that we have taken. And then after that, the second derivative also, if you recollect, it was presented as p double dash of 0, which becomes 6 of p naught minus 2p1 plus p2. It's nothing but the substitution that I have done here. P double dash of 1, which is equal to 6 p1 minus 2p2 plus p3. If I have to go back and look at the values for you, we had written it as p double dash of 0 is equal to n minus 1 p2 minus p1 minus p1 minus p naught. So in our case it is 3 into 2, so it is p2 minus p1 minus p1 if I remove the bracket plus p naught. So this it becomes 6 into p naught minus 2p1 plus p2. If I write similarly, p double dash of 1, which is equal to n into n minus 1, which was written as pn minus 2 minus pn minus 1 minus p of n minus 1 minus pn. So if I substitute the value, I'll get it as this as 6 p1 minus here 3 minus 1, which becomes p2. If I remove the bracket, this becomes minus p2 after removing the bracket, and minus p3. So if I further readjust it, I'll get it as p1 minus 2p2 minus, sorry, this minus into minus, it becomes plus, so this becomes p3. So that is what we have written previously. This is the double derivative or the parametric second derivative. So now let us see how to write the matrix representation for this. Or or you can also call it as the matrix formulation of the Bezier function, which is obtained by expanding the polynomial expression for the blending functions. So now let me just restructure this. So it can be written as p of u is equal to u cube, u square, u and 1 into the matrix of Bezier curve, and this should be further multiplied into the points. So here I have, it should be written into the points, which is nothing but I have P0, P1, P2 and P3. So what exactly is this M? So I'll say M Bezier, that is the matrix, which is equal to minus 1, 3, minus 3, 1, 3, minus 6, 3, 0. I mean, here I'm only substituting the values which we had got. So 0 and 1, 0, 0 and 1. So these are the points that you need to recollect while drawing the Bezier curve. Thank you. Don't get confused. This is the calculations that you had done in the previous equations. You only have taken the values of it and written it here. Hope all of you have understood the concept of Bezier curve. Thank you.